Just like the strong acid versus strong base titration curve, in the weak acid versus strong base titration curve, we have also looked at a similar set of points. We have looked at the first point whereby we've calculated the pH of our weak acid solution without having added any NaOH. We have also calculated the pH of the solution after adding some NaOH, and we have also now calculated the pH of the solution after we have added an equal number of moles of base to that of the acid. So in this video, we are going to now take a look at the calculation of our solution after an excess amount of base have been added to our solution. So the example that we are going to work on is very similar to the one that we did for the strong acid versus strong base. Again, we're going to be adding 120 milliliters of a 0.1 molar NaOH solution. And it is added to 100.0 milliliters of a 0.1 molar CH3COOH solution. So the first thing we do is the stoichiometric calculation. So CH3COOH, and we add it to the NaOH, and we end up with NaCH3COO plus H2O. Now once again, we use our modified ice chart, and we end up with 0.0100 moles of our CH3COOH, 0.01200 moles of NaOH, and we start off with 0 amount of our salt, NaCH3COO, as well as 0 amount of H2O. Again, we take a look and we can see that our acetic acid is now the limiting reagent. And so in reacting, it will be used up. And so finally, we have no acid left over. We have 0.00200 moles of NaOH remaining. We have 0.01000 moles of sodium acetate remaining, and we have 0.01000 moles of H2O formed. Again, when we take a look, we can say that the water is not going to be involved because we are in a solution where the solvent is water. Now in this analysis over here, we see that we have two materials that could potentially produce OH being formed. So the first one is our strong base, which is the NaOH. So in this case, the NaOH over here is a strong base, and so it dissociates 100%, and so we can say that the OH concentration is directly related to NaOH, and so we can then calculate the concentration, and we now have 0.00200 moles of OH divided by 0.2200 liters, and so we end up with a concentration of 9.1 times 10 to the minus 3. However, if we examine the salt that is formed over here, we see that the Na is from the NaOH. And once again, our analysis is that since the NaOH is a strong base, the Na is not going to want to undergo any further reaction, and so Na is a spectator ion. However, when we take a look at the CH3COO, what we find that it comes from a weak acid. And so in this case over here, because the CH3COOH is a weak acid, that means the CH3COO, or the acetate ion, is going to want to undergo a reaction with water. And so therefore we need to take into account its concentration. And so in this case we have our CH3COO minus. And I write this without the Na because the Na is my spectator ion. And so we have 0.01000 moles, and we divide it by the total volume, and we end up with a concentration of 4.5 times 10 to the minus 2. Now in this case, there is two potential scenarios. One is that the excess conjugate base will have no effect on the final pH, and one where the excess conjugate base is going to have an effect on the final pH. So let us mathematically examine to see whether the excess conjugate base is going to affect the final pH. So I'm going to calculate two scenarios. So in scenario 1, I am going to assume the excess CH3COO minus has no effect. So therefore, essentially, the concentration of the OH is dictated by just the presence of the excess NaOH, and therefore the OH is going to determine what the pH will be. So in this case, the OH concentration is going to equal to 9.1 times 10 to the minus 3 molar. So the POH over here is going to be negative log 9.1 times 10 to the minus 3, which is equal to 2.04. So the pH over here is going to be 14.00 minus 2.04, which is equal to 11.96. Note that this value is exactly the same as that of the strong acid versus strong base titration curve. Now, in the second scenario, we're now going to assume excess CH3COO minus has an effect. So if this is the case, there is going to be a reaction whereby the acetate is going to produce new OH ions. So we have to write our equation in the following way. CH3COO minus is going to react with water, and it's going to be in equilibrium with the acid, CH3COOH, plus the OH minus. Now, if you take a look, we have an equilibrium, so we use our ice chart. And so if we take a look at the concentration, we have the concentration of the excess CH3COO minus, which is 4.5 times 10 to the minus 2. We don't care about water. At present, we do not have any acetic acid. Now, in terms of the OH, remember that we have excess NaOH, and so therefore the concentration of the OH is from the NaOH. So 9.1 times 10 to the minus 3. So according to Le Chatelier's principle, the equilibrium will shift to the right. So therefore you're going to have minus x plus x plus x. So you end up with 4.5 times 10 to the minus 2 minus x. Then you're going to just have x, and then you're going to have 9.1 times 10 to the minus 3 plus x. So because we generate a base, we're now going to need to use the Kb expression in order to calculate the x that is generated. So the Kb over here is going to be 1.0 times 10 to the minus 14. And it's going to be divided by the Ka, and we get 5.6 times 10 to the minus 10. So now as we now calculate the expression, we're going to have 5.6 times 10 to the minus 10 is equal to x times 9.1 times 10 to the minus 3 plus x all over 4.5 times 10 to the minus 2 minus x. Now as you can see, because the initial concentration is significantly bigger than the Kb, we can now say that this X over here, which is added, is very small. And we can also see that this X over here is also very small. We cannot eliminate this X because the operation here is a multiplication. So if we calculate this out, what we end up with is X is equal to 2.8 times 10 to the minus 9 molar. And it is equal to the concentration of the OH added. Now, what is significant here is that if we were to take a look at the amount of OH, this is the amount of OH that is added by the reaction of CH3COO minus with water. And the question is, does this make a significant difference? Well, let's examine the OH from the NaOH. So now, if we compare the amount of OH added by the excess NaOH, we have 9.1 times 10 to the minus 3 molar. Whereas when we take a look at the amount of OH added by the reaction of our conjugate base of the weak acid, we have a value of 2.8 times 10 to the minus 9 molar. As you can see, this amount is negligible. As a result, when we take a look at our calculation, we can basically assume that the pH of the solution after the equivalence point is controlled by the excess NaOH, and therefore we do not have to worry about this equilibrium. And so to summarize, when we take a look at the calculation whereby our NaOH is in excess over here, the pH of the final solution can be calculated by scenario 1, whereby we only look at the OH that comes from the NaOH that is in excess. Therefore, our calculations are now simplified.